Okay, here is example number 8 of chapter 3, section 3. We're doing the increasing, decreasing intervals and first derivative test. So for example 8, for both of the functions below, determine the intervals of increasing and decreasing and the x coordinates of any relative extrema and justify. So this is what we need to ask ourselves first. Is f of x continuous? If you ask yourself this question every time, you won't miss any of the little details that don't necessarily stand out when you don't have a graph to look at. So the answer to this is no, it's not continuous. Look what you've got here. If I take f of x and I factor the numerator, I can take an x out. I'm left with x squared plus 1 all over x. And so I can cancel this x and this x. So that means that there is a point of discontinuity at x equals 0. So this function is not continuous. If you cancel those x's out, it's just going to be, it's going to look like a parabola, actually, with a vertex at 0, 1. And so the point of discontinuity is also at 0. So if this is 0, 1 right here, there'd be an open circle right here, and it would go up like this and go up like this. That's what that graph is going to look like, okay? So we are not going to have a continuous graph. So x equals 0 is going to be one of your critical values. So now we're going to do when the derivative equals 0 and where the derivative may not exist. Okay, so we can go back to f of x equals x cubed plus x all over x, and you can simplify that. You can break it up. You can leave it like what we had up above. I think I will leave it like what we had up above just to keep the same thinking. So x squared plus 1, just to rewrite this because you can't see it very well. So you're left with x squared plus 1. So if I take the derivative of that, your derivative is going to be 2x. Okay, now we're going to set this equal to 0. So 0 equals 2x, divide by 2, and I should cancel it that way. So x equals 0. Now, if we had a parabola, like if we truly just had a parabola that didn't have a point of discontinuity, x equals 0 would be a spot where the derivative would equal 0, because this would be the vertex and it would be this nice, like flat tangent line. So that's why we're coming up with x equals 0 again. But we know that there's actually a point of discontinuity at x equals 0. So we're going to keep that in mind when we do our intervals. The derivative is going to exist everywhere but x equals 0, so we don't have to worry about doing that again. What we do need to do is make our number line. So we put 0 down. We test points to the left, we test points to the right into the derivative. We make sure that that makes sense compared to what we know our graph is going to look like. So we plug into the first derivative anything less than 0. Put anything less than 0 in for x, you're going to get negative. So downward slope. Anything greater than 0, you're going to get something positive here. Times 2 is also going to be positive. So like that. This should make sense with what we see for our graph, right? Our slope here is negative. Our slope here is positive. So we should see those same results when we do a first derivative test. So we are decreasing from negative infinity to 0. We are increasing from 0 to positive infinity. And the second part of this was the x coordinates of the relative extrema. You have a relative extremum at x equals 0, but since x equals 0 is not in the domain, no relative extrema exist. Okay, remember when we canceled, here we go. I didn't realize you couldn't see all that. There you go. At x equals 0, but since x equals 0 is not in the domain, no relative extrema exists. When we canceled these x's out, we pulled that value out of the function. So x equals 0 no longer is part of the domain. We can't have x equal to 0. Otherwise, you would have a 0 in the denominator of a fraction, and that is not possible. So the spot where we would have had a relative minimum actually doesn't exist because x equals 0 is not part of our domain. This is negative because the first derivative is negative. This is a positive slope because the first derivative gives you a positive answer. Okay, so that's part A. Part B, same idea kind of with part B, only we can't factor out an x, so we don't have a point of discontinuity. Instead, we have a vertical asymptote at x equals 0. Okay, nothing cancels here. So, but we do need to take the derivative. I'm sorry, not the derivative. We do need to take the denominator and set that equal to 0. So you're going to have a vertical asymptote. So that means x equals 0 is going to be one of your critical points. Let's see. Let's actually take the derivative now. So we're looking for where the derivative is going to be equal to 0 and where the derivative does not exist. All right, so I'm going to rewrite this just to help me out a little bit here. So this is going to be, let's see, so the whole thing is negative. So it'll be negative x to the 4th over x squared. And then minus, you would have to distribute that negative to both, 1 over x squared. And by writing it like this, will allow me to rewrite it like this. So negative x squared minus x to the negative 2. Well, that's a lot of negatives and 2's. There you go. So now I can carefully use power rule. So the derivative would be negative 2x plus 2x to the negative 3rd, which would be negative 2x plus 2 over x to the 3rd, like that, because the 2 is not being raised to the negative 3rd, just the x is. Well, we can see that the derivative, this, is not going to exist at x equals 0, which comes back to that vertical asymptote, so that should make sense. So we already have that listed as a critical value. I'm not going to list it again, but we do need to combine these so that we can set the derivative equal to 0. The only time you can set the numerator equal to 0, the only time you can set the numerator equal to 0 is if you combine it into one fraction. So we need to combine this into one fraction. So let's see, this will be all over x cubed. This will be negative 2x to the 4th, and this will be just plus 2. So we're going to set this equal to 0. Only set the numerator equal to 0. So negative 2x to the 4th plus 2 equals 0. Let's see, what can we do here? Subtract 2, or you could factor out a 2, either one. Negative 2x to the 4th equals negative 2. I'm going to divide by negative 2. So x to the 4th equals 1. Take the 4th root of both sides. So this is x. The 4th root of 1 is just 1. And so that's going to be x equals 1. So your other critical value will be at 1, and then the first critical value we had was at 0. So now we're going to use first derivative test, put it on a number line. So this is 0 and 1. Choose some values less than 0, some values in between 0 and 1, and some values greater than 1. Remember, we're plugging them into the first derivative. So we can use this expression right here for our first derivative. If you put something negative in, anything negative to the 4th power is positive. Let's see here. This would be positive, and then negative 2 times a positive number would be negative, and then plus 2 could also be negative. So let's see, and then this would be negative, so this will be positive right here. So this is going up. Between 0 and 1, this would be a really small positive number. Times negative 2 would be a negative number. Plus 2, remember this is going to make this even smaller, so this will be positive. Over a positive number is also positive. And then greater than 1, 2 to the 4th power, like we could use 2. That's going to be positive times negative 2 is going to be negative. This is going to be a really big number. Plus 2 will still be a negative number. And then all over a positive number. So this will be negative. So you are going to have intervals of increasing from negative infinity to 0. Make sure you stop at 0 and then list it again, 0 to positive infinity. The reason we have to break this up is because at 0, we had that vertical asymptote. So it is not continuous through here. We need to have two different intervals, one for the left-hand side of the asymptote and one for the right-hand side. Then we are decreasing from 1 to positive infinity. Since we are increasing and then decreasing, f prime of x is changing signs. That means you have a relative maximum at x equals 1. And there you go. Hope that helped, everybody.